Beneath the rigid crust of the densest objects in the known universe, something extraordinary may be happening. Inside a neutron star, where matter is crushed to densities beyond anything we can recreate on Earth, where a single teaspoon of material would outweigh an entire mountain, there may exist a fluid that flows without any friction at all. A quantum fluid, threaded by billions of microscopic whirlpools, each one thinner than an atom, spinning in perfect unbroken formation. And when those whirlpools suddenly shift, even slightly, the entire star lurches. Its rotation jumps in a fraction of a second, and we can detect that jump from thousands of light years away. This may be the largest quantum phenomenon in the observable universe. And tonight, we're going deep inside to understand exactly how it works. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with a dying star, because that is where every neutron star begins. Not with a gentle fading, not with a slow dimming over billions of years the way our sun will eventually wind down. A neutron star is born from catastrophe, from one of the most violent events the universe has to offer. And to understand what is happening inside a neutron star, to understand how something as delicate as a quantum superfluid could possibly exist inside an object, this extreme, we first need to understand how these objects come to exist in the first place. Picture a massive star, something at least 8 times heavier than our sun. A star like this might be 20 or 30 times wider than the sun, blazing with a luminosity tens of thousands of times greater. From the outside, it looks majestic, stable, powerful, but deep in its interior, a clock is ticking. Massive stars live fast and die young. While a star like the sun can burn steadily for about 10 billion years, a star 8 or 10 times heavier burns through its fuel in just 10 or 20 million years, spending its reserves at a furious rate. For millions of years, this star has been a furnace, fusing lighter elements into heavier ones in its core. It started with hydrogen, the simplest element, fusing it into helium. When the hydrogen ran out in the core contracted, heated up, and began fusing helium into carbon. When the helium ran out, the core contracted again and started fusing carbon into neon. Then neon into oxygen. Then oxygen into silicon. Each stage burns hotter and faster than the last. Hydrogen burning lasted millions of years. Helium burning lasted maybe 1 million. Carbon burning might last a few thousand years, oxygen burning a few years, and silicon burning, the final stage, lasts only about a single day. The star is racing toward the end, accelerating with every step. By this point, the core has become a layered structure, like an onion, with concentric shells of progressively heavier elements surrounding the center. Hydrogen burning continues in the outermost shell, helium burning underneath, carbon below that, and so on, all the way down to the innermost shell where silicon is fusing into the heaviest element the star will ever produce, iron. And iron is where the road ends. Every element lighter than iron releases energy when it fuses. That released energy is what holds the star up against the crushing weight of its own gravity. The outward pressure from fusion balances the inward pull of gravity, and the star remains stable. But iron sits at the very bottom of the nuclear binding energy curve. Fusing iron into anything heavier does not release energy. It absorbs energy. It takes energy away from the core instead of providing it. So when the core fills with iron, the star has built itself a dead end. It has created a core made of the one element that cannot sustain it any further. The furnace has produced its own poison. For a brief moment, the iron core is held up by something called electron degeneracy pressure. This is a quantum mechanical effect that connects directly to the quantum phenomena we are going to explore later. Electrons obey a fundamental rule of quantum mechanics called the Pauli exclusion principle, which says that no two electrons can occupy exactly the same quantum state in the same place at the same time. Each electron must have its own unique combination of position and momentum. When matter is compressed to extreme density, the electrons are squeezed closer and closer together. They resist this squeezing because they are running out of available quantum states. This resistance creates a pressure, a quantum mechanical pressure that has nothing to do with temperature or the motion of particles in the ordinary thermal sense. It is purely a consequence of quantum rules. And for a while, this degeneracy pressure is enough to support the iron core against gravity. But the core is growing. More silicon keeps fusing in the shell above, raining more iron down onto the pile. The iron core grows heavier and heavier, and eventually it crosses a critical threshold, about 1.4 times the mass of our Sun. This is a limit first calculated in the 1930s by the Indian astrophysicist Subramanian Chandrasekhar. Beyond this mass, electron degeneracy pressure is simply not strong enough. The electrons cannot push back hard enough to resist gravity, and gravity wins. What happens next takes less than a single second. The core collapses at speeds approaching a quarter of the speed of light, roughly 70,000 kilometers per second. In that fraction of a second, it goes from being roughly the size of Earth to something only about 20 to 25 kilometers in diameter, a sphere roughly the size of a city. The collapse is so fast and so violent that it heats the core to temperatures of over 100 billion degrees. The density spikes beyond anything that exists anywhere else in the universe, except inside other neutron stars and black holes. In that fraction of a second, the core becomes so dense that electrons are literally forced into protons, combining through a process called inverse beta decay to form neutrons. Each merger also produces a neutrino, a ghostly particle that barely interacts with matter. The collapse produces a flood of these neutrinos, trillions upon trillions of them, carrying away an almost unimaginable amount of energy. In fact, the neutrinos carry away roughly 99% of all the energy released during the collapse. The visible explosion that follows, spectacular as it is, accounts for only a tiny fraction of the total energy output. The outer layers of the star slam into this newly formed ball of neutrons. The core is now so dense and stiff that the infalling material bounces off it, creating a shock wave. That shock wave, energized by heating from the absorbed neutrinos and driven by complex fluid instabilities that physicists are still working to fully simulate, pushes outward through the star. The outer layers are blown apart in a supernova explosion, so bright that for a few weeks the dying star can outshine an entire galaxy of hundreds of billions of stars. If you could gather up all the light and energy released during the visible explosion alone, it would exceed the total energy output of our Sun over its entire 10 billion year lifetime. And that visible energy is less than 1% of the total energy released. The neutrinos carry the rest. What is left behind at the center, sitting in the expanding cloud of glowing debris, is a neutron star. An object typically containing somewhere between about 1.4 and roughly 2 times the mass of our Sun, all compressed into a sphere roughly 20 kilometers across. Let that scale sink in for a moment. The mass of our entire Sun, a ball of plasma 1,390,000 kilometers in diameter, has been crushed into something that could fit comfortably inside the boundaries of a single city. If you scooped up a single teaspoon of neutron star material and somehow brought it to Earth, that teaspoon would weigh somewhere around 4 billion tons, more than the combined weight of every car, truck, ship, and airplane humans have ever built. All of it. In one teaspoon. A neutron star's surface gravity is roughly 200 billion times stronger than Earth's. If you dropped a small object from a height of 1 meter above the surface, it would strike that surface traveling at roughly 7 million kilometers per hour. Light leaving the surface has to fight so hard against this gravity that it loses a measurable fraction of its energy, shifting toward redder wavelengths as it climbs out of the gravitational well. Time itself runs measurably slower at the surface, compared to empty space far away. If you could somehow survive on the surface and look outward, the intense gravity would bend light from behind the star around toward your eyes, allowing you to see more than half the star's surface at once. Geometry itself is distorted. These are not theoretical abstractions or science fiction scenarios. These are measured consequences of general relativity applied to real objects that astronomers observe and study routinely. And there are 2 more properties of neutron stars that emerge directly from the violence of their birth. 2 properties that will matter enormously for everything we discuss later. The first is rotation. The second is magnetism. Both are consequences of a simple but powerful principle. When something large collapses into something small, the properties it already had become amplified to extremes. Consider rotation first. The massive star that produced the neutron star was already rotating, just slowly. Most large stars take weeks or months to complete a single turn on their axes. Our own Sun rotates roughly once every 25 days at its equator. But angular momentum, the physical quantity that measures rotational motion, is conserved. When the core collapses, the total angular momentum does not change. It cannot change unless something external acts to remove it. What changes is the size of the object carrying that momentum. And the relationship between size and spin rate is dramatic. When a spinning object contracts, it spins faster. This is the same physics behind a figure skater pulling their arms inward during a spin. The arms move closer to the axis, the moment of inertia decreases, and the skater accelerates, spinning faster and faster without pushing off anything. No extra energy is added. The spin rate simply increases because the mass has moved closer to the rotation axis. Now apply this to a collapsing stellar core. The original core might have been the size of Earth, roughly 12,700 kilometers across, rotating perhaps once every few seconds. After the collapse, it is 20 kilometers across. The radius has decreased by a factor of roughly 600. And because the spin rate scales with the square of that contraction factor, the rotation increases enormously. A core that turned once every few seconds before collapse now spins dozens of times per second after collapse. Some neutron stars are born spinning even faster, hundreds of times per second, depending on the initial angular momentum of the core and how much was carried away by the expelled material during the supernova. This is why pulsars pulse, The neutron star is spinning, and its beams of radiation sweep past Earth, with each revolution like the beam of a lighthouse. The magnetic field undergoes a similar amplification. The progenitor star had a magnetic field, modest by neutron star standards, perhaps a few hundred or a few thousand Gauss, but magnetic flux, like angular momentum, is approximately conserved during the collapse. The total magnetic flux threading through the core stays roughly the same, but the area through which it passes shrinks by that same factor of 600 squared, roughly 360,000. The magnetic field strength is inversely proportional to the area, so the field is amplified by a factor of hundreds of thousands. A modest stellar field of a few thousand Gauss becomes a neutron star field of 1 trillion Gauss or more. Some neutron stars, called magnetars, have fields reaching 1,000 trillion Gauss, though additional amplification mechanisms such as a dynamo process during the first seconds of the star's life may contribute to those extreme cases. These magnetic fields are strong enough to distort the shapes of atoms at a distance, and would be lethal to any complex chemistry at ranges of thousands of kilometers. And crucially for our later discussion, this magnetic field threads through the interior of the star, through the same dense quantum fluid that fills the core. How that fluid interacts with the field, how superconducting protons organize that field into quantized structures, is a question that lies at the heart of neutron star physics. So a neutron star is not merely dense, it is dense, rapidly spinning, and intensely magnetized. All three properties are consequences of the same gravitational collapse, and all three will turn out to be essential for understanding the extraordinary quantum behavior hidden beneath the surface. Now, here is where many people make a critical mistake in how they picture these objects. They hear the name neutron star, and they imagine a solid ball of neutrons packed together motionlessly, like marbles crammed into a jar, frozen in place, inert, static. Just sitting there under the weight of gravity, doing nothing interesting. But that picture is wrong. It is dramatically, fundamentally wrong. A neutron star is not a uniform lump of identical particles locked in place. It is one of the most complex, dynamic, and physically rich objects in the entire universe. It has real internal structure, distinct layers with different compositions, different physics, and different behavior. And those layers matter enormously for what we are about to explore. So let's go inside, layer by layer, starting at the surface and working our way down into conditions that no laboratory on Earth has ever come close to reproducing. The outermost layer of a neutron star is called the outer crust. If you could somehow approach the surface, which you cannot because the gravity would crush you and the magnetic fields would tear apart your atoms long before you arrived, you would find a solid surface, not liquid, not gas, solid. The outer crust is made of atomic nuclei, primarily iron and elements near iron on the periodic table, arranged in a rigid crystalline lattice. Picture something like an incredibly dense metal, a regular repeating structure of heavy nuclei sitting in a sea of free electrons that flow between them. This is not so different in principle from a block of iron on your desk at home. In everyday iron nuclei sit in a lattice held together by shared electrons. The outer crust of a neutron star follows the same basic idea, but the density is millions of times higher, and the nuclei are packed incomparably tighter. This outer crust is relatively thin, perhaps only a few hundred meters deep in some models, possibly up to about 1 kilometer. But even in this thin shell, the density is already staggering by any earthly standard. At the very surface, the density sits at roughly 1,000,000 grams per cubic centimeter, about 1,000,000 times denser than water. A single sugar cube-sized piece of this crust material would weigh roughly 1,000 tons on Earth. And as you move deeper into the crust, the density climbs rapidly, the pressure rises, and as these conditions intensify, something important starts to change in the composition of the matter. Deeper into the crust, the pressure becomes so intense that the nuclei are forced to absorb electrons from the surrounding sea. Each absorbed electron converts a proton inside the nucleus into a neutron. This means the nuclei become increasingly neutron-rich as depth increases. They contain far more neutrons relative to protons than any stable nucleus found naturally on Earth. These are exotic isotopes, things like nickel-78 or krypton-118, or even more neutron-heavy configurations. Species that would decay in a tiny fraction of a second under normal conditions, but are stabilized here by the immense pressure squeezing everything together. These exotic nuclei still sit in a crystalline lattice, arranged in an orderly repeating structure, but their internal composition has become increasingly unusual, stretched far beyond anything familiar from the terrestrial chemistry. And then, something truly remarkable happens. At a density of roughly 400 billion grams per cubic centimeter, roughly 400 billion times the density of water, we cross a boundary that physicists call the neutron drip line. At this critical density, the nuclei have absorbed so many extra neutrons that they simply cannot hold anymore. Their nuclear binding energy cannot accommodate another neutron. So the neutrons begin to leak out. They drip out of the nuclei and start to fill the space between them as a free fluid. Not locked inside any nucleus. Not bound to any particular lattice site. Free to move through the spaces between nuclei. This is the beginning of the inner crust. And it is a genuinely strange and fascinating environment. Picture it. You still have a crystalline lattice of neutron-rich nuclei, an ordered, rigid structure. But now those nuclei are surrounded by and immersed in a sea of free neutrons that have escaped their nuclear confinement. These free neutrons flow between the nuclei. They are not frozen in place, they are mobile. And as we are going to discover, when the temperature drops low enough, these free neutrons can enter a quantum state that transforms the behavior of this entire region. But we will come back to that. The inner crust extends perhaps another kilometer or two below the outer crust. And as the density keeps climbing, the nuclei themselves begin to change shape in ways that physicists find both fascinating and slightly amusing. Under the competing influences of the strong nuclear force pulling nucleons together, the electromagnetic repulsion between protons pushing them apart, and surface tension effects at the boundary of each nucleus, the spherical nuclei begin to deform. Theoretical calculations predict that the nuclei elongate into rods, flatten into sheets, form cylindrical tubes, and eventually merge into interconnected three-dimensional structures with holes and channels running through them. Physicists have nicknamed these configurations nuclear pasta because the shapes genuinely resemble types of Italian food. There is a predicted layer of gnocchi, small rounded lumps, a layer of spaghetti, where nuclei stretch into long thin rods, a layer of lasagna, where they flatten into broad parallel sheets, a layer of anti-spaghetti, where instead of rods of nuclear matter in the sea of neutrons, you get cylindrical tunnels of empty space bored through solid nuclear material, and variations in between. This is not a humorous aside. Nuclear pasta is a serious prediction from theoretical nuclear physics, studied using advanced computational simulations. The competition between the relevant forces at these densities creates a complex energy landscape where different geometric arrangements become energetically favorable at different depths. The exact sequence of pasta phases and the precise densities at which each appears remain debated, because no laboratory on Earth can approach these conditions. But some calculations suggest that nuclear pasta may be among the strongest materials in the universe, possibly billions of times stronger than steel. Breaking those structures means overcoming the strong nuclear force at densities where that force is operating at its most effective range. It would take extraordinary energy to shatter nuclear lasagna. Below the inner crust, we enter the outer core, and this is where the majority of the neutron star's mass actually lives. The outer core extends from the base of the crust down several kilometers, filling the bulk of the star's interior. The density here has climbed above roughly 200 trillion grams per cubic centimeter. That is approximately the density of matter inside an atomic nucleus itself. And at this density, the individual nuclei that existed in the crust can no longer survive as separate objects. Their surfaces have been crushed together. The boundaries between one nucleus and the next have dissolved. What remains is a continuous fluid of individual nucleons, neutrons and protons, no longer organized into distinct nuclei, but flowing freely as a dense quantum liquid. Mixed in with them are electrons, and at higher densities, muons, heavier cousins of the electron. This is not a solid, it is a liquid. But it is unlike any liquid you have ever encountered or ever will encounter on Earth. The particles are packed so tightly that every neutron, every proton, is essentially touching its neighbors on all sides, interacting through the strong nuclear force with every particle around it simultaneously. This liquid is composed mostly of neutrons, roughly 90 to 95% by number, with the small admixture of protons and electrons making up the remaining few percent. The exact proportions depend on density and on the details of how the strong nuclear force operates in bulk matter at these conditions. Details that physicists are still refining through a combination of theory, heavy ion collision experiments, and astronomical observation. Now here is something critical. This outer core is hot when the star is first born. A freshly formed neutron star has an interior temperature of several 100 billion degrees in the first moments of its existence. The core is a screaming furnace of nuclear matter, but it cools down remarkably fast. Those neutrinos we talked about earlier, the ghostly particles produced in enormous quantities during the collapse, continue to be generated inside the core through various nuclear processes. And neutrinos can escape the star almost freely because they interact with matter so weakly that even the incredible density of a neutron star barely slows them down. They stream outward through the star and carry energy away into space. This neutrino cooling is phenomenally efficient. Within minutes of the star's formation, the core temperature drops from hundreds of billions of degrees to around 10 billion degrees. Within the first few years, it falls to about 1 billion degrees. Within a few thousand years, the interior temperature may have dropped to roughly 100 million degrees. And over the following tens of thousands to hundreds of thousands of years, it continues falling. The star is still incredibly hot by any earthly standard. 100 million degrees is far beyond anything we experience in everyday life. But by neutron star standards, by the standards of the nuclear physics governing the behavior of matter at these densities, this temperature is getting cold. And this cooling has consequences that nobody expected when neutron stars were first predicted. Consequences that change the nature of the matter inside the star in a profound and astonishing way. But understanding those consequences requires us to look even deeper first. Below the outer core, at the very center of the star, lies the inner core. And this is where our confidence in what we know begins to break down. At the center of a neutron star, the density may reach 5 to 10 times the density of a normal atomic nucleus. This translates to somewhere around 1 billion grams per cubic centimeter. These are conditions that exist nowhere else in the observable universe outside neutron stars, and the instance before matter falls into a black hole. And crucially, there is no laboratory on Earth that can squeeze matter to these densities. The most powerful particle accelerators in the world, facilities like the Large Hadron Collider near Geneva, can create temperatures high enough to briefly produce quark-gluon plasma, the state of matter that existed microseconds after the Big Bang. But those experiments produce hot, low-density plasma. They cannot produce the cold, ultra-dense matter that exists in the inner core of a neutron star. Those conditions are inaccessible to direct experiment. They are unique. And because we cannot recreate those conditions, we do not know for certain what matter does when compressed this far beyond nuclear density. There are several competing theoretical predictions, and physicists have spent decades debating which is correct. The honest answer is that we still do not know. One possibility is that the matter remains as neutrons and protons, the same nuclear fluid as the outer core, just denser. If this is the case, the inner core is simply a continuation of the outer core, with no dramatic change in composition. But most physicists suspect something more interesting happens. A second possibility is that entirely new particles appear. At sufficiently high density, it becomes energetically favorable for some neutrons to transform into heavier particles called hyperons. Hyperons are members of the baryon family, like neutrons and protons, but they contain one or more strange quarks in addition to the up and down quarks found in ordinary nucleons. Under normal conditions, hyperons are deeply unstable, decaying in tiny fractions of a second. But in the crushing pressure of a neutron star's inner core, the energy required to maintain neutrons at the top of their Fermi sea becomes so large that converting a neutron into a lower energy hyperon actually lowers the total energy of the system. If this happens, hyperons would form a stable population alongside the neutrons and protons. This changes the equation of state, the fundamental relationship between pressure and density, in ways that affect how massive a neutron star can grow before it collapses into a black hole. A third possibility is more exotic still. Neutrons and protons are not fundamental particles. Each one is composed of 3 quarks bound together by the strong force, mediated by particles called gluons. Under normal conditions, those quarks are confined, permanently locked inside their parent nucleon. But at extreme density, theoretical models suggest the boundaries between individual nucleons may blur, soften, and eventually dissolve. The quarks could become deconfined, free to move across the entire core rather than being imprisoned inside individual neutrons and protons. If this happens, the inner core would contain quark matter, a phase of matter fundamentally unlike anything ever directly observed. Some models predict a sharp transition from nuclear matter to quark matter. Others predict a smooth crossover. Others predict a mixed phase where bubbles or droplets of quark matter coexist with regions of nuclear matter in an arrangement that, ironically, might resemble the nuclear pasta of the crust, but at a much deeper level. There are still other proposals. Some theories predict condensates involving particles called kaons. Others invoke color superconducting phases where quarks themselves form pairs. The diversity of theoretical predictions reflects the depth of our uncertainty about this region. What we do know is that whatever is happening at the center of a neutron star, it must obey the laws of quantum mechanics and quantum chromodynamics in conditions we cannot probe directly. The inner core is one of the great unsolved frontiers of fundamental physics. So here's where we stand. A neutron star is not a simple object. It is layered, structured, and extraordinarily complex. An outer crust of crystalline nuclei sitting in an electron sea. An inner crust where free neutrons drip out of swollen, neutron-rich nuclei and flow between them through possible phases of nuclear pasta. An outer core of continuous neutron-proton-electron quantum liquid at densities matching or exceeding the density inside an atomic nucleus. And an inner core whose very composition remains one of the deepest open questions in modern physics. Each layer has different particles, different interactions, different behavior under pressure. The neutron star is an entire world of extreme physics compressed into a 20-kilometer ball, and this entire ball, this layered sphere with more mass than the sun, is spinning. Many neutron stars rotate hundreds of times every second. Some spin more than 700 times per second. At those rates, the surface of the star is moving at a measurable fraction of the speed of light, and the interior, that dense quantum liquid of neutrons and protons and whatever else resides at the center, is spinning with it. But as the neutron star cools, as those neutrinos carry energy away, and the temperature drops year after year, century after century, the particles in the core begin to do something remarkable. Something that seems almost impossible at first glance. Something that was first predicted in the late 1950s and that physicists have been working to understand ever since. The temperature falls below a critical threshold, and when it does, the neutrons and protons in the interior begin to pair up. They form delicate quantum partnerships, correlated states that span the entire fluid. And when enough of them have paired, the fluid undergoes a transformation. Friction vanishes. Viscosity disappears. The fluid begins to flow in a way that has no classical analog. It becomes something that should not exist in a place this violent, this dense, this extreme. It becomes a superfluid. And understanding how that happens, why it happens, and what it means for the behavior of the entire star is exactly where we are headed next. We have arrived at the edge of something extraordinary. A neutron star, born screaming in the fire of a supernova, has been cooling. Neutrinos are streaming away from its interior, carrying energy into the void. The temperature that once reached hundreds of billions of degrees has been falling for centuries, for millennia. And at some point during that long cooling, the matter inside the star begins to change. Not in what it is made of. The particles remain the same. Neutrons, protons, electrons, all still present. What changes is how those particles behave. They stop acting like independent individuals and begin to act collectively. They form pairs. And when enough of them have paired, the fluid they compose enters a quantum state that transforms the entire interior of the star. To understand how this happens, we need to take a detour. We need to leave the neutron star for a moment and talk about something that was discovered here on Earth, in laboratories, in ordinary metals, at temperatures far colder than anything you would encounter in daily life. We need to talk about superconductivity, because the physics that makes a neutron star's interior behave the way it does was first understood not in astrophysics, but in condensed matter physics, in the study of how electrons behave inside metals cooled to near absolute zero. The story begins in 1911 when the Dutch physicist Heike Kamerlingh-Onnes was experimenting with mercury cooled to just a few degrees above absolute zero, roughly minus 273 degrees Celsius, the lowest possible temperature. Onnes was measuring how the electrical resistance of mercury changed as it got colder. Normally, as you cool a metal, its resistance drops gradually. Electrons flowing through the metal collide with vibrating atoms in the crystal lattice, and those collisions create resistance. As the metal gets colder, the atoms vibrate less, so there are fewer collisions and the resistance decreases. Onnes expected a smooth, gradual decrease. What he found instead shocked him. At a temperature of about 4.2 Kelvin, just over 4 degrees above absolute zero, the resistance of mercury did not just decrease, it vanished completely. It dropped to exactly zero. Not almost zero, not very small, zero. He could send an electric current flowing through the mercury, and that current would continue flowing forever with no energy loss whatsoever. No resistance at all. He had discovered superconductivity. This was deeply puzzling. In normal physics, in classical physics, there is always some resistance. Electrons always lose some energy when flowing through a material. The idea that resistance could drop to literally zero seemed to violate basic thermodynamic expectations. Something fundamentally new was happening, but it took nearly half a century before anyone understood what that something was. The explanation came in 1957 from 3 American physicists, John Bardeen, Leon Cooper, and Robert Schrieffer. Together they developed what is now called BCS theory, named from their initials. Its key insight is one of the most beautiful and counterintuitive ideas in all of physics. It has to do with pairing. Here is the puzzle. Electrons are negatively charged, like charges repel each other. 2 electrons brought close together push each other apart. So the idea that electrons might pair up, might form bound partnerships, seems absurd on its face. Why would 2 particles that repel each other choose to link together? The answer lies in the crystal lattice of the metal itself. As an electron moves through a metal, it pulls slightly on the positively charged atomic nuclei that make up the lattice. The electron is negative, the nuclei are positive, so there is an attractive force. The electron tugs the nearby nuclei very slightly toward itself as it passes. This creates a tiny region of slightly higher positive charge density in the lattice, a fleeting distortion that appears and disappears as the electron moves through. But that tiny region of extra positive charge can attract a second electron. The first electron has created, through its interaction with the lattice, an indirect attractive force that a second electron can feel. This interaction is mediated by vibrations in the lattice called phonons. The first electron disturbs the lattice, creating a phonon. The second electron absorbs that phonon, feeling the effect of the distortion the first electron created. The result is a weak, but real attractive interaction between 2 electrons, An attraction that is not direct but indirect, communicate through the lattice. And at low enough temperatures, when the thermal energy of the system is small enough that it cannot disrupt this delicate attraction, the two electrons form a pair. These pairs are called Cooper pairs, named after Leon Cooper, who first showed mathematically that such pairing is possible. And Cooper pairs are strange objects. They are not like molecules. They are not two electrons orbiting each other in close proximity like two atoms bound in a molecule of water or carbon dioxide. The two electrons in a Cooper pair can be separated by enormous distances compared to the spacing between atoms. In a typical superconductor, the two electrons in a pair might be hundreds or even thousands of atomic spacings apart. There are millions of other electrons and atoms between them, and yet they are correlated. They share a quantum connection. They move through the lattice as a coordinated partnership. Their momenta linked, their quantum states entangled. This is a crucial point that will matter when we return to the neutron star. A Cooper pair is not a little molecule. It is not two particles stuck together like two magnets. It is a quantum correlation, a relationship between two particles that can be very far apart but are nonetheless connected through the rules of quantum mechanics. Their collective behavior, the way their momenta and spins are connected, is what matters. And that collective behavior changes everything. When electrons form Cooper pairs, something remarkable happens to the fluid of electrons as a whole. The pairs, unlike individual electrons, behave as bosons. This is a technical but essential distinction. In quantum mechanics, particles come in two fundamental types. Fermions, which include electrons, protons, and neutrons, obey the Pauli exclusion principle. No two identical fermions can occupy the same quantum state. This is why electrons in an atom fill up successive energy levels rather than all piling into the lowest one. Bosons, on the other hand, are not restricted by the Pauli principle. Any number of identical bosons can occupy the same quantum states simultaneously. An individual electron is a fermion. It has a quantum property called spin equal to 1/2. But a Cooper pair, made of two electrons each with spin 1/2, has a combined spin that is an integer, either 0 or 1 depending on how the spins align. And particles with integer spin are bosons. So Cooper pairs are composite bosons. And because they are bosons, they can all condense into the same quantum state. They can all fall into the lowest available energy level simultaneously, forming what physicists call a condensate. This condensate behaves as a single coherent quantum entity. It is not a collection of individual pairs acting independently. It is one unified quantum state stretching across the entire material. And a condensate like this has extraordinary properties. Because all the pairs are in the same quantum state, they move together. They cannot be scattered individually by lattice vibrations or impurities the way single electrons can. To scatter one pair, you would have to break it apart, which requires a minimum amount of energy, a quantity called the energy gap. At low temperatures, where the available thermal energy is smaller than this gap, nothing in the system has enough energy to break a pair. So the pairs flow without scattering. Without scattering, there is no resistance. The current flows forever. This is superconductivity. Now, here is where we return to the neutron star. Because in the late 1950s, shortly after BCS theory explained superconductivity in metals, physicists began to ask a daring question. Could something similar happen inside a neutron star? Could the neutrons and protons in that ultra-dense quantum liquid form their own version of Cooper pairs? The idea sounds almost absurd at first. A neutron star's interior is nothing like a metal. There is no crystal lattice. There are no phonons in the traditional sense. The particles involved are not electrons, but nucleons, neutrons, and protons, which are thousands of times heavier than electrons. The forces involved are not electromagnetic, but nuclear, governed by the strong nuclear force, the most powerful of the four fundamental forces of nature. Everything is different, and yet the underlying quantum mechanics is the same. The principle that allows pairing does not depend on the specific details of the attraction. It depends only on three things. First, you need fermions, particles that obey the Pauli exclusion principle. Neutrons and protons are fermions. Second, you need an attractive interaction between those fermions, regardless of what mediates that attraction. And third, you need a low enough temperature that thermal energy cannot disrupt the pairs once they form. Let's examine each of these. Neutrons and protons are fermions with spin 1/2. That condition is automatically satisfied. What about the attractive interaction? In metals, the attraction between electrons is indirect, mediated by lattice phonons. In neutron star matter, the attraction between nucleons comes from the residual strong nuclear force. This is the force that holds atomic nuclei together in ordinary matter. At very short range, the strong force between two nucleons is intensely repulsive. Push two neutrons too close together and they resist fiercely. But at slightly larger separations, the force becomes attractive. It pulls them toward each other. This attraction is what binds protons and neutrons together inside atomic nuclei. And this same attraction, operating between free neutrons in the outer core of a neutron star, can serve the same role that lattice phonons serve in a metal. It provides the glue for Cooper pairing. The details are more complex than in a metal, because the nuclear force is far richer and more complicated than the electromagnetic interaction. The nuclear force depends on the distance between particles, on their relative orientations, on their spins, and on the density of the surrounding medium. At low densities, like those found in the inner crust and the outermost parts of the outer core, the attractive part of the nuclear force between two neutrons is strongest in what physicists call the singlet S0 channel. This is a pairing state where the two neutrons have opposite spins and zero orbital angular momentum. Their spins cancel, giving a total spin of 0, and they pair in a spherically symmetric configuration. This type of pairing is called S-wave pairing, and it is the simplest and most robust form of Cooper pairing, directly analogous to what happens in most conventional superconductors. But as the density increases deeper into the outer core, the situation changes. At higher density, the neutrons are packed more tightly. They are forced closer together on average, and at very short range, the nuclear force becomes repulsive. This repulsion weakens and eventually destroys the S-wave pairing channel. The singlet S0 pairing that works well at lower densities is suppressed at high density, but another pairing channel can open up. At higher densities, neutrons may pair in the triplet P2 channel. This is a more complex configuration where the two neutrons have parallel spins, giving a total spin of 1, and they orbit each other with 1 unit of angular momentum. The paired state is no longer spherically symmetric. It has a more complicated shape, and the physics governing it is considerably harder to calculate. The exact density at which S-wave pairing gives way to P-wave pairing, and the exact strength of the P-wave pairing at various densities are among the most actively debated questions in neutron star physics. Different theoretical calculations, using different models of the nuclear force and different many-body techniques, give different answers. Some models predict that the P-wave energy gap is large enough to produce robust superfluidity deep in the core. Others predict it is very small, perhaps too small to matter at the temperatures neutron stars actually reach. The honest answer is that we do not know with certainty which pairing channel dominates at which density, or how strong the pairing is throughout the interior. What about protons? Protons in the outer core are also fermions, and they also experience the attractive nuclear force. But protons are present in much smaller numbers than neutrons, typically making up only about 5 to 10% of the nucleons by number. They move through a sea dominated overwhelmingly by neutrons. Despite being a minority population, protons can also form Cooper pairs, and because protons are charged particles, their Cooper pairing does not produce a superfluid. It produces a superconductor. Just as electron Cooper pairs in a metal allow electric current to flow without resistance, proton Cooper pairs in a neutron star would allow electric currents to flow without resistance through the star's interior. Proton pairing is generally expected to occur in the singlet S0 channel, similar to low-density neutron pairing. The critical temperature for proton superconductivity, the temperature below which pairs form, is estimated to be in the range of roughly 100 million to a billion Kelvin for densities in the outer core. These are not everyday temperatures by any stretch, but remember, a neutron star's interior cools to these temperatures within decades to centuries after birth, so proton superconductivity could establish itself relatively early in a neutron star's life. Now let me explain what the critical temperature actually means, because it is central to whether superfluidity and superconductivity actually occur. Every pairing state has a characteristic energy scale called the energy gap. This gap represents the minimum energy required to break a Cooper pair apart into two unpaired particles. If the thermal energy available in the system, which is proportional to the temperature, is larger than this gap, then the constant thermal jostling will keep breaking pairs apart as fast as they form. No stable condensate can develop, but if the temperature drops below a critical value, if the thermal energy becomes smaller than the gap, then pairs can form faster than they are broken. A condensate builds up, and the superfluid or superconducting state is established. For neutron S-wave pairing in the inner crust and lower density outer core, the critical temperature is estimated at roughly 500 million to a billion Kelvin. For proton S-wave pairing, the estimates are broadly similar. For neutron P-wave pairing deeper in the core, the estimates are much more uncertain, ranging from tens of millions to several hundred million Kelvin, depending heavily on which theoretical model you use. Here is why this matters practically. A newly born neutron star has an interior temperature of tens of billions of degrees, far too hot for any pairing. But within years, decades, or at most a few centuries, the interior cools through these critical temperatures. And as it does, pairing switches on. First in the regions where the critical temperature is highest, then spreading to regions with lower critical temperatures. These superfluid and superconducting phases do not appear everywhere simultaneously. They grow, expanding through the interior as the star cools. Different layers of the star enter the paired state at different times, depending on local density and the corresponding critical temperature. And this is where I need to correct a common misconception. It will be easy to hear all of this and conclude that the entire neutron star becomes one uniform superfluid, a single homogeneous quantum state from crust to core. That is not what happens. The interior is layered. Different regions have different compositions. Different regions have different pairing channels. Different regions have different critical temperatures and different energy gaps. The free neutrons in the inner crust may pair in the S-wave channel, forming a superfluid that permeates the lattice of neutron-rich nuclei. The neutrons in the lower density outer core may also pair in the S-wave channel. Deeper in the outer core, neutrons may switch to P-wave pairing with a different gap and different properties. Protons throughout the outer core may form a separate superconducting condensate with their own pairing gap. And at the very center of the star, in the inner core, we genuinely do not know what happens. If exotic particles like hyperons are present, their pairing properties are almost completely unknown. If quark matter exists, quarks might form their own paired states through a mechanism called color superconductivity, but the details are highly speculative. The inner core is a frontier of ignorance, so the picture is not one uniform superfluid. It is a patchwork, a mosaic of different quantum phases at different depths, each with its own pairing symmetry, its own energy gap, its own critical temperature, and its own response to rotation and magnetic fields. The neutron star's interior is a layered quantum system of extraordinary complexity. There is something else I need to clarify, because it is a source of frequent confusion. Superfluidity does not mean that the fluid has absolutely no interactions, no friction, and no dissipation under all circumstances. That is an oversimplification. What superfluidity means is that below the critical temperature, the fluid can flow without viscosity in certain situations. Specifically, the superfluid component can move without dissipation as long as the flow velocity stays below a critical threshold. If the flow is too fast, or if the superfluid is disturbed too violently, the paired state can be disrupted locally, and dissipation can occur. There are also processes that allow energy exchange between the superfluid component and normal unpaired particles even below the critical temperature. These processes are weaker than in a normal fluid, sometimes much weaker, but they are not zero. Superfluidity reduces dissipation dramatically. It does not eliminate all interactions entirely. This distinction will matter enormously when we discuss how the superfluid interior interacts with the rigid crust of the star. Let me also say a word about what makes neutron star superfluidity so remarkable. Compared to superfluidity we observe in laboratories on Earth, we have observed superfluidity in two systems on Earth. One is helium-4, the common isotope of helium, which becomes a superfluid below about 2.2 Kelvin, roughly minus 271 degrees Celsius. Helium-4 atoms are bosons, so they do not need to form Cooper pairs. They can condense directly into the same quantum state because they already satisfy both statistics. The other is helium-3, the rarer isotope, which becomes a superfluid below about 2.5 millikelvin, 2.5 thousandths of a degree above absolute zero. Helium-3 atoms are fermions, like neutrons. They must form Cooper pairs to become superfluid, and they do, pairing through an attraction mediated by the magnetic interactions between their nuclear spins. Helium-3 superfluidity, discovered in 1972, was in many ways the closest laboratory analog to what theorists were predicting should happen inside neutron stars. The helium-3 pairs even form in a p-wave channel, similar to the p-wave pairing predicted for neutrons at higher densities in the core, but the scale is utterly different. Laboratory superfluids exist at temperatures within a few degrees or a few millidegrees of absolute zero. Neutron star superfluidity, if it exists as predicted, occurs at temperatures of hundreds of millions of degrees. The energy gaps are millions of times larger. The densities are trillions of times higher. The volumes involved are not cubic centimeters in a laboratory cryostat, but cubic kilometers inside a collapsed star. If the theoretical predictions are correct, the superfluid inside a neutron star is the largest and most extreme example of a macroscopic quantum state in the known universe. A quantum phenomenon operating not at the scale of atoms or molecules, but at the scale of an entire astronomical body. And this is the central wonder that drives everything we are about to explore. A neutron star is a macroscopic quantum object. Not in some vague metaphorical sense, in a precise physical sense. The interior contains a condensate, a coherent quantum state that extends across kilometers. Billions upon billions of neutrons, each one correlated with a partner, each pair participating in the same collective wave function. The superfluid is not a collection of individual pairs acting independently. It is one system, one quantum state, spread across the entire core of a collapsed star. And this quantum state has consequences. It changes how the star rotates. It changes how the star cools. It changes how the star's magnetic field behaves. It changes how the star responds to external forces. And most dramatically, it creates the conditions for sudden, violent events that we can actually detect from thousands of light years away. Events called glitches. Events that may be telling us indirectly about the quantum state of matter under conditions that no experiment on Earth can reach. But to understand how those glitches happen, we first need to understand something that seems paradoxical. How does a superfluid rotate? Because in one sense, a superfluid should not be able to rotate at all. The very property that defines it, the absence of viscosity, the resistance to any form of internal friction, means that a superfluid cannot rotate the way an ordinary liquid does. If you spin a bucket of water, the water inside spins too, dragged along by friction with the walls of the bucket. If you spin a bucket of superfluid, the superfluid ignores the bucket. It sits still while the walls spin around it. It does not rotate. It cannot rotate in the ordinary sense. And yet, neutron stars rotate. They spin. Some of them spin hundreds of times per second. Their interiors must somehow participate in that rotation. If the superfluid simply sat still while the crust spun around it, the two would quickly fall catastrophically out of synchronization, and we would see effects far more dramatic than anything actually observed. So how does a superfluid reconcile its quantum nature with the reality that the star is spinning? The answer involves one of the most elegant and strange phenomena in quantum physics. And it is where we are going next. We are left with a paradox. A superfluid, by its very nature, resists ordinary rotation. If you try to spin a container of superfluid the way you would spin a bucket of water, the superfluid does not follow. Ordinary water rotates because internal friction, viscosity, transmits the spinning motion from the walls of the bucket inward through the fluid. Layer drags on layer. The walls drag the outermost layer, which drags the next layer, and so on, until the entire body of water is spinning together. But a superfluid has no viscosity. There is no friction between layers. There is nothing to transmit the rotation inward. The container spins. The superfluid sits still. It simply refuses to participate. This was observed directly in laboratory experiments with superfluid helium-4 in the middle of the 20th century. Researchers cooled helium below its critical temperature, placed it in a rotating container, and watched. The container spun. The superfluid did not. It remained motionless, indifferent to the walls spinning around it. A normal fluid always eventually follows the rotation of its container. A superfluid does not. And yet, neutron stars rotate. They spin rapidly. Many of them complete a full revolution in a fraction of a second. The fastest known pulsars rotate more than 700 times per second, meaning their surfaces are moving at a significant fraction of the speed of light. Their interiors, including the dense superfluid that fills the outer core and saturates the inner crust, must somehow participate in this rotation. If the superfluid simply sat motionless while the crust spun at hundreds of revolutions per second, the mismatch would be catastrophic. Angular momentum would not balance. The star's behavior would be fundamentally different from what we observe. So how does a superfluid rotate? The answer is one of the most elegant solutions nature has devised. A superfluid does not rotate the way a normal fluid does. It cannot rotate as a smooth, continuous flow. Instead, it rotates by forming vortices, tiny, discrete, quantized whirlpools. Each one carries a fixed, specific amount of rotational motion, and together, an enormous array of these vortices allows the superfluid to mimic the rotation of a solid body while remaining, at the microscopic level, irrotational everywhere except at the vortex cores themselves. Let me explain what this means. In classical physics, when a bucket of water rotates, the water at the edge moves fastest and the water near the center moves slowest. There is a smooth, continuous gradient of rotational speed from the center to the rim. The velocity field varies smoothly across the fluid. This is called solid body rotation, and it is how ordinary fluids and solids behave when they spin. A superfluid cannot do this. The quantum mechanical wave function that describes the condensate, the single coherent state in which all the Cooper pairs participate, imposes a strict mathematical constraint. In the bulk of the superfluid, away from any special structures, the flow must be irrotational. This means the fluid velocity cannot curl. It cannot form the kind of smooth, continuous rotational pattern that a normal fluid adopts. If you calculated the mathematical quantity called the curl of the velocity field at any point in the bulk superfluid, you would get zero. The superfluid, in its bulk, is not rotating at all. It is locally stationary everywhere. This seems to make rotation impossible, but nature finds a way around the constraint through a loophole. The irrotational condition applies everywhere the superfluid wave function is well defined. But the wave function does not have to be well defined everywhere. It is allowed to have singular points, lines where the wave function drops to zero, where the condensate is locally destroyed, where the superfluid order parameter vanishes. Along these lines, the irrotational constraint does not apply. And along these lines, the superfluid can circulate. These lines are called quantized vortices, and they are extraordinary objects. A quantized vortex is a thread of rotational motion embedded in an otherwise non-rotating superfluid. Picture a long, incredibly thin filament running through the fluid. Right at the center of this filament, the superfluid condensate is destroyed. The Cooper pairs are broken apart. The core of the vortex is a tiny tube of normal, unpaired matter. Outside this core, the superfluid swirls around the filament, circulating in the same direction, like water swirling around a drain. But unlike an ordinary whirlpool, where the circulation speed and size can vary continuously, a quantized vortex carries a fixed, discrete amount of circulation. The circulation cannot take any arbitrary value. It is quantized. It comes in indivisible units. The amount of circulation each vortex carries is set by fundamental constants. For a superfluid made of paired neutrons, each vortex carries exactly one quantum of circulation. This quantum is determined by Planck's constant divided by twice the mass of a neutron. The factor of 2 appears because the superfluid is composed of Cooper pairs, each containing 2 neutrons, and it is the pair that acts as the fundamental unit of the condensate. This quantity, this single quantum of circulation, is incredibly small. It is a fixed universal number that cannot be changed or adjusted. Every neutron vortex in the universe carries exactly this much circulation. No more, no less. The core of each vortex, the region where the condensate is destroyed and the matter is in its normal unpaired state, is extremely thin. Calculations suggest the core radius is on the order of the coherence length of the condensate, which in the inner crust might be roughly 10 to 100 Fermis. A Fermi is a million billionth of a centimeter. These vortex cores are thinner than an atomic nucleus. They are among the thinnest physical structures that can exist in nature, and yet they thread through the entire star, running from one side to the other, each one a filament of quantized rotational energy stretching across kilometers. Now here is where the mathematics becomes beautiful. If each vortex carries only a tiny fixed amount of circulation, and the star needs to rotate at some particular rate, then the star must contain an enormous number of vortices. The total rotation of the superfluid is the sum of the contributions from all the individual vortices. More vortices mean faster rotation. Fewer vortices mean slower rotation. The superfluid adjusts its rotation rate by adjusting the number of vortices it contains. How many vortices are we talking about? The number depends on how fast the star is spinning. For a pulsar rotating about 10 times per second, which is fairly typical, the superfluid interior contains roughly 100 trillion vortices. Let me say that again. 100 trillion. 100 million individual quantum whirlpools threading through the star's interior. For a millisecond pulsar spinning several hundred times per second, the number climbs into the quadrillions. These vortices are not scattered randomly. They arrange themselves into a remarkably orderly pattern. In a uniformly rotating superfluid, the vortices space themselves evenly, forming a regular triangular lattice. They stand roughly parallel to the rotation axis, like a forest of impossibly thin trees, all pointing in the same direction. The spacing between adjacent vortices depends on the rotation rate. A faster spinning star has more vortices packed more closely together. A slower spinning star has fewer vortices spaced further apart. For a pulsar spinning about 10 times per second, the average spacing between neighboring vortices works out to roughly 1/100th of a centimeter. That sounds small by everyday standards, but compared to the vortex core itself, which is smaller than an atomic nucleus, the spacing is enormous. The vortices are incredibly sparse relative to their own thickness. The superfluid between them is essentially undisturbed, flowing irritationally, not rotating at all in the local sense. It is only when you zoom out, when you average over millions or billions of vortices, that the combined effect of all those tiny circulations adds up to give the same rotation rate as the crust. This is how a superfluid rotates, not through smooth, continuous bulk motion, not through viscous coupling that drags layer upon layer, but through a discrete lattice of quantized vortices, each carrying one indivisible unit of circulation, collectively mimicking solid body rotation when viewed from afar. From a distance, the superfluid appears to be spinning uniformly. But up close, at the microscopic level, it is doing something completely different. It is threading itself with trillions of quantum whirlpools, each one a tiny singularity in the condensate, each one carrying a fixed portion of the star's total angular momentum. This idea was first proposed theoretically for superfluid helium by Lars Onsager in 1949 and independently developed by Richard Feynman in the 1950s. It was confirmed experimentally in rotating helium in laboratory studies during the 1960s. And when theorists began to apply these ideas to neutron stars in the 1960s and 70s, they realized that quantized vortices were not just possible inside a neutron star. They were inevitable. Any rotating superfluid must contain them. And since neutron stars are both superfluid and rotating, vortices must be present. Trillions of them, threading through the core like an immense microscopic scaffolding of angular momentum. Now comes the part that sets the stage for everything that follows. Because these vortices do not simply exist passively inside the star, spinning freely, adjusting their number and spacing without constraint. Something happens to them in certain regions of the star. Something that creates tension. Something that builds stress over time. Something that eventually leads to a sudden and dramatic release. In the inner crust of the neutron star, remember, we have a crystalline lattice of neutron-rich nuclei immersed in a sea of free superfluid neutrons. The vortex filaments threading through the superfluid must pass through this lattice. And when they do, they interact with the nuclei. The vortex core, that tiny tube of unpaired normal matter at the center of each vortex, can become attracted to the nuclear lattice sites. The energy of the system can be lowered if the vortex core sits on top of a nucleus or near it. Because the nucleus is already a region of high nucleon density, and accommodating the vortex core there requires less disruption to the surrounding superfluid. This phenomenon is called vortex pinning. The vortices become pinned to the lattice. They attach themselves to the crystal structure of the crust, like threads snagged on a rough surface. Once pinned, a vortex does not move easily. It is held in place by an energy barrier. To move the vortex away from its pinning site requires overcoming that barrier, supplying enough force to tear the vortex free from the nucleus it is anchored to. The exact strength of pinning, how tightly each vortex is held, how much force is needed to unpin it, depends on details of the nuclear interaction between the vortex core and the lattice nuclei. These details are not fully understood. Different theoretical calculations give different estimates of the pinning force, sometimes differing by orders of magnitude. But the general picture is well established and broadly accepted. In the inner crust of a neutron star, vortices can pin to the nuclear lattice. And this pinning has profound consequences for the star's rotation. Here is why. A neutron star that we observe as a pulsar is losing rotational energy. Pulsars emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep through space like a lighthouse. Every time a beam sweeps past Earth, we detect a pulse. That is how pulsars got their name. But generating and maintaining these beams costs energy. The star radiates energy away into space through magnetic dipole radiation, and through the charged particles, it accelerates along its magnetic field lines. This energy comes from the star's rotational kinetic energy. As the star radiates, it slows down. It loses angular momentum. The rotation rate gradually decreases, and the pulses arrive slightly less frequently over time. This slowdown is measurable. Astronomers can track pulsar timing with extraordinary precision, using radio telescopes to record the arrival time of each pulse. Over months and years, they can measure the rate at which the rotation is slowing. For the Vela pulsar, for example, one of the most studied pulsars in the sky, the rotation rate decreases by a tiny but measurable amount each day. The Vela pulsar currently spins about 11.2 times per second. Its rotation period increases by roughly 1.6 trillionths of a second every second. That sounds negligibly small, but radio astronomers can measure timing to such extraordinary precision that even this minute change is detected clearly. Now, here is the critical question. When the crust slows down, what happens to the superfluid inside? If the superfluid were a normal fluid, coupled to the crust by viscosity, the answer would be simple. The crust slows down, viscous friction transmits that slowdown to the fluid, and the fluid slows down along with it, staying in step. The entire star decelerates together as one unit. But the superfluid is not coupled to the crust by ordinary viscosity. It has no viscosity. The superfluid component in the inner crust and core does not feel the crust's deceleration directly through friction. The only way the superfluid can slow down is by reducing its number of vortices. Remember, the superfluid's rotation rate is determined by how many vortex lines thread through it. Faster rotation means more vortices. Slower rotation means fewer. To spin down, the superfluid must eliminate vortices. They must move outward through the star and eventually leave, reducing the total circulation and lowering the rotation rate. In a normal superfluid, in a laboratory container, this is exactly what happens. When you slow down the container, the vortices gradually drift outward toward the walls and annihilate there. The superfluid adjusts its rotation smoothly to match the container. There is a slight lag, a brief delay, but the vortices move freely and the adjustment happens relatively quickly. But inside a neutron star, the vortices are pinned. They are anchored to the crystal lattice of the inner crust. They cannot move freely outward. They are stuck. And if the vortices cannot move, the superfluid cannot reduce its vortex count. And if the superfluid cannot reduce its vortex count, it cannot slow down. The superfluid remains spinning at its original rate, oblivious to the fact that the crust above it is decelerating. This is the central mechanism. This is the key to everything that follows. The crust is slowing down. The superfluid is not. A difference in rotation rate develops between the two components. The crust, coupled to the external magnetic field and losing energy through radiation, decelerates steadily. The superfluid, its vortices pinned to the lattice and unable to migrate outward, maintains its faster rotation. A rotational lag builds. At first, this lag is tiny. The crust slows by a trillionth of a second per second in its period. After a day, the difference in rotation rates between crust and superfluid is almost imperceptible. After a week, it is still minuscule. After months, it is small but growing. The superfluid is spinning just slightly faster than the crust, and with each passing moment, the difference grows a little more. Think of it like this. Imagine two wheels initially spinning at the same rate, lock together. Now unlock them and apply a brake to one wheel, the crust, while leaving the other wheel, the superfluid, free. The braked wheel slows down. The free wheel keeps spinning. The difference in their speeds grows steadily over time. Now, imagine that the two wheels are connected not by a rigid axle, but by elastic bands. As the speed difference grows, the elastic bands stretch. Tension builds. The bands pull harder and harder, trying to bring the two wheels back into alignment. In the neutron star, the role of those elastic bands is played by the pinning forces. The vortices are anchored to the lattice. The lattice is part of the crust. The crust is decelerating. The superfluid wants to keep spinning at its original rate. The vortices are caught in the middle, connecting the slowing crust to the faster spinning superfluid. They are under stress. The pinning forces are holding them in place against a growing rotational mismatch. This stress is real. It is a physical force acting on each vortex, a force that grows as the rotational lag between crust and superfluid increases. Physicists call this the Magnus force, named after the 19th century physicist Heinrich Magnus, who first studied forces on spinning objects in flowing fluids. When a vortex is embedded in a superfluid that is flowing past it, a sideways force acts on the vortex, perpendicular to both the vortex axis and the direction of the flow. In the neutron star context, the flow past the vortex arises because the superfluid is rotating faster than the lattice to which the vortex is pinned. The velocity difference between superfluid and crust creates a flow relative to the vortex, and this flow exerts a Magnus force that pushes the vortex outward, toward the equator of the star. If the vortex were free, not pinned, it would respond to this force by drifting outward. As vortices move outward, the total circulation enclosed within the star decreases, and the superfluid's effective rotation rate drops, bringing it closer to the crust's rate. This would provide smooth coupling between superfluid and crust. The spin down would be gradual, continuous, and boring. But the vortices are pinned. They do not drift freely. The Magnus force pushes on them, but the pinning force holds them in place. As long as the Magnus force remains smaller than the maximum pinning force, the vortices stay put. The rotational lag continues to grow. The stress continues to build. Energy is being stored in the rotational mismatch between the superfluid and the crust, like energy being stored in a compressed spring. This cannot continue indefinitely. There is a limit. The pinning force has a maximum strength. It can hold the vortex in place against a certain amount of stress, but not infinite stress. As the rotational lag grows and the Magnus force increases, eventually the force on the vortices exceeds the maximum pinning force, and when that threshold is crossed, the vortices break free. They unpin, and when they unpin, they do not drift gently outward. They move suddenly, rapidly, many of them at once. This is the moment. This is the trigger. The accumulated stress has grown beyond what the lattice can sustain. Vortices unpin, possibly in a cascade where the unpinning of one vortex disturbs its neighbors and triggers further unpinning. A wave of vortex motion sweeps through a region of the inner crust. Vortices that have been locked in place for months or years suddenly shift outward, carrying their quanta of angular momentum with them. And that angular momentum goes somewhere. It goes to the crust. The angular momentum that was stored in the superfluid's excess rotation, locked in place by the pinned vortices and inaccessible to the crust for all those months or years, is suddenly released. It transfers to the crust, and the crust, receiving this sudden injection of angular momentum, speeds up. Its rotation rate jumps, not by much, not by a dramatic amount, but by a measurable amount. A pulsar that was steadily slowing down suddenly, in less than a minute, sometimes in a matter of seconds, starts spinning faster. This is a glitch. An observed, measured, documented event where a pulsar's rotation rate abruptly increases by a tiny but detectable amount. We see it in the timing data as a sudden decrease in the pulse period, a jump in the spin frequency, an interruption in the otherwise smooth and predictable slowdown. The pulsar has been decelerating steadily for months or years. Then, in an instant, it lurches forward. It spins up. And then it begins decelerating again, settling back into its steady slowdown, waiting for stress to build again, waiting for the next glitch. This is the physical chain we were asked to trace. The neutron star cools below its critical temperatures. Nucleons pair into superfluid or superconducting states. The superfluid's rotation is organized into trillions of quantized vortices. Those vortices pin to the crystal lattice in the inner crust. The crust decelerates through electromagnetic radiation while the pinned superfluid maintains its rotation. A lag develops. Stress builds on each pinned vortex as the Magnus force grows. Eventually the stress exceeds the pinning threshold. Vortices unpin and move. Angular momentum transfers from superfluid to crust, and the visible star suddenly spins faster. It is a chain that begins with quantum mechanics, with the pairing of neutrons in a dense nuclear fluid, and ends with a macroscopic event visible across thousands of light years. A quantum phenomenon producing an astronomical observable. And it is happening in real pulsars that astronomers monitor every day. But there are complications. There are subtleties. The picture I have just described, clean and elegant as it is almost certainly not the whole story. The real physics is messier. The vortices in the core, deeper in the star below the inner crust, may not pin at all. They may be free to move, coupled to the crust only through a weak friction that allows gradual angular momentum transfer, rather than sudden events. The exact mechanism by which vortices unpin, whether it is a thermal process where random fluctuations occasionally kick a vortex free, or a collective mechanical failure where an entire sheet of vortices gives way simultaneously, remains actively debated. Some models suggest the glitch trigger is not unpinning at all, but a sudden cracking of the crust itself, a starquake that rearranges the lattice and forces vortices to move. Other models propose that interactions between the neutron vortices and the proton flux tubes in the superconducting component create additional forces that influence vortex motion. The interplay between these mechanisms, the relative importance of pinning in the crust versus coupling in the core, the role of the superconducting protons, the possibility of crust fracture, all of these remain open questions. Different pulsars show different glitch behaviors. The Vela pulsar produces large glitches at semi-regular intervals, roughly every 2 to 3 years, each one increasing the spin frequency by a similar amount. The Crab pulsar produces smaller, more frequent glitches with different recovery patterns. Other pulsars glitch rarely or not at all. This diversity suggests that glitch behavior depends on the individual star's internal properties, its mass, temperature, magnetic field strength, and the detailed structure of its crust and core. No single simple model explains all observed glitches. But the broad picture, the essential mechanism of superfluid vortices interacting with the crust and episodically transferring angular momentum, is supported by decades of observational evidence and theoretical work. It remains the leading framework for understanding pulsar glitches, and the implications extend far beyond just explaining a timing anomaly. Because if this picture is correct, then every glitch we observe is a message from inside the neutron star. A signal from the quantum interior leaking out through the star's rotation. An indirect window into conditions that no telescope can image and no laboratory can reproduce. A window into the largest quantum system in the universe. And understanding what happens after the glitch, how the star recovers, how the superfluid and crust recouple, and what all of this tells us about the extreme physics hidden beneath the surface is where we are going next. On the 11th of January, 1969, something happened to the Vela pulsar that nobody was expecting. This neutron star, sitting roughly 1,000 light-years away in the southern constellation Vela, had been spinning steadily, decelerating at a predictable rate as it radiated energy through its magnetic field. Astronomers have been tracking it carefully, recording the precise arrival time of each radio pulse. The timing was extraordinarily stable, predictable down to millionths of a second, and then, in an instant, it jumped. The rotation frequency increased abruptly. The pulsar, which had been gradually slowing down for as long as anyone had observed it, suddenly sped up. The spin frequency increased by roughly 1 part in a million. That sounds tiny, and in absolute terms, it is tiny. But for an object as massive as a neutron star, containing more mass than the Sun compressed into a sphere 20 kilometers across, a sudden increase of 1 part in a million in spin frequency represents a colossal transfer of angular momentum. The energy involved is enormous. Something deep inside the star had lurched. This was the first observed pulsar glitch, and it shattered the assumption that pulsars were perfect clocks, whose rotation only decreased smoothly over time. Something inside the neutron star was capable of storing rotational energy and releasing it suddenly. Something hidden beneath the surface was communicating with the visible crust through a violent, impulsive mechanism. Since that first detection, astronomers have observed hundreds of glitches across dozens of pulsars, and the patterns are revealing. The Vela pulsar remains one of the most prolific and consistent, producing large glitches roughly every 2 to 3 years. Each glitch increases the spin frequency by a similar fractional amount, roughly 1 part in a million. The regularity is remarkable. It suggests a repeating cycle where stress builds at a roughly constant rate and is released when a consistent threshold is exceeded, very much in line with the vortex unpinning picture we developed. The Crab pulsar, embedded in the famous Crab Nebula, about 6,500 light-years away, behaves differently. The Crab glitches more frequently than Vela, but its glitches are much smaller. Typical Crab glitches are roughly 1,000 times smaller in fractional size than typical Vela glitches. The recovery after each glitch is also different. These differences are important because they tell us that the internal conditions vary between stars. The Crab pulsar is younger than Vela, hotter, and spinning faster. It has a stronger magnetic field. All of these factors influence the properties of the superfluid, the strength of vortex pinning, the extent of the region where pinning occurs, and the dynamics of how angular momentum is exchanged. The fact that different pulsars glitch differently is not a failure of the theory. It is a feature. It tells us that glitches are sensitive probes of the interior, and that each star's individual properties leave their mark on the observed behavior. there is another pulsar that deserves mention. A fast-spinning young pulsar in the Large Magellanic Cloud that glitches with unusual regularity, producing moderate-sized glitches approximately every 100 days. Its behavior is so regular that astronomers have used it to test models of vortex accumulation and release. The near-clockwork timing of its glitches supports the idea that stress builds linearly between events and is released when a threshold is crossed, exactly as the vortex pinning model predicts. But observing the glitch itself, the sudden spin-up, is only half the story. What happens afterward is equally important, because after the initial jump, the pulsar does not simply continue decelerating at its previous rate from its new, slightly higher frequency. Instead, it enters a recovery phase, a complex multi-timescale relaxation, where parts of the spin-up are gradually reversed and the star settles back toward its long-term, slow-down trend. This recovery is where we see the fingerprints of mutual friction, the mechanism by which the superfluid and the crust interact and gradually recouple after being thrown out of equilibrium by the glitch. Here is what happens. The glitch itself, the sudden unpinning and outward motion of vortices, transfers angular momentum from the superfluid to the crust, spinning the crust up. But this transfer does not instantaneously bring the entire superfluid and crust into perfect rotational alignment. Different regions of the star respond on different timescales. The inner crust, where vortices have just unpinned, may recouple relatively quickly as vortices repin to new lattice sites or as the remaining pinned vortices adjust to the new rotational state. The outer core, where the superfluid may be less strongly pinned or not pinned at all, responds through a weaker form of coupling called mutual friction. Mutual friction is not ordinary viscosity. Remember, the superfluid has no viscosity in the conventional sense, but it is not completely decoupled from the normal matter in the star either. The vortex cores, those thin threads of normal unpaired matter at the center of each vortex line, do interact with the surrounding charged particles, specifically with the electrons and the protons that coexist with the dominant neutron superfluid. As a vortex moves through the mixture of particles, its normal matter core scatters off electrons. These electrons in turn interact with protons. And if the protons form a superconductor, they carry magnetic flux in quantized tubes that also interact with the vortex cores. All of these interactions create a drag force on the vortex, a friction that is not between layers of fluid in the classical sense, but between the vortex lines and the other components of the star's interior. It may help to think of it this way. Imagine you have a pool of water and you drop a fine mesh screen horizontally into it. If you try to push the screen sideways through the water resists. It drags on the mesh. The mesh drags on the water. Energy is exchanged. Now imagine replacing the water with a superfluid. If the mesh were perfectly smooth, the superfluid would pass through without any drag at all. No friction, no resistance. The screen would glide through as though the fluid were not there. But the vortex lines are not a smooth mesh. They are singular structures with normal matter cores, and those cores interact with the charged particles in the surrounding medium. So the mesh, in this analogy, is slightly rough. Not rough enough to create the enormous viscous drag you would get in a normal fluid, but rough enough that there is a weak, measurable friction as the vortex lines move relative to the other components. That is mutual friction. It is far weaker than ordinary viscosity. weak enough that the superfluid can maintain a rotational lag against the crust for months or years, but strong enough that, given sufficient time, it gradually nudges the two components back toward spinning at the same rate. This mutual friction is what allows the superfluid and crust to communicate rotationally, even in the absence of ordinary viscosity. It is much weaker than normal viscous coupling would be, which is why the superfluid can maintain a rotational lag for months or years without being dragged into alignment with the crust. But it is not zero. Over time, mutual friction acts to bring the superfluid and crust back toward co-rotation. After a glitch, when the crust has been spun up and a new rotational mismatch has been created in the opposite sense, mutual friction gradually transfers angular momentum back, allowing the crust to relax partially toward its pre-glitch deceleration trend. The timescales of this recovery are diagnostic. Astronomers observe that post-glitch recovery happens in stages. There's typically a fast component that relaxes within hours or days, and a slower component that takes weeks or months. Some glitches show even longer recovery timescales extending over years. Each timescale corresponds to a different region of the star with different coupling strength. The fast recovery likely corresponds to regions where mutual friction is relatively strong, perhaps in the outer core where vortices are free and coupling is efficient. The slow recovery corresponds to regions where the coupling is weaker, perhaps deeper in the star or in regions where vortex pinning creates a more complex interaction. By carefully measuring these recovery timescales and comparing them to theoretical models, physicists can constrain the properties of the superfluid. They can estimate how strong the mutual friction is in different parts of the star. They can infer how much of the star's moment of inertia is carried by the superfluid component that participated in the glitch. For the Vela pulsar, studies of the glitch sizes and the fraction of angular momentum involved suggests that the region responsible for the glitch contains at least 1 to 2% of the star's total moment of inertia. This is consistent with the inner crust superfluid being the primary reservoir, though some models suggest that a portion of the outer core may also contribute. This brings us to a deeper point. Glitches are not just interesting anomalies. They are tools. They are one of the very few ways we have to probe the interior of a neutron star. We cannot see inside. We cannot send a probe. We cannot recreate the conditions in a laboratory. But the star's rotation carries information about what is happening inside. Every glitch, every recovery timescale, every pattern of glitch sizes and intervals is a piece of data about the internal structure, about the extent and strength of superfluidity, about the properties of the crust, about the coupling between different layers. Glitches are indirect evidence. They do not give us a direct image of the superfluid or a photograph of quantized vortices, but they give us constraints. They narrow the range of possible internal structures. They tell us what the inside must be like in order to produce the behavior we observe. Now let me turn to another consequence of superfluidity that goes beyond rotation. Because the superfluid state does not just change how the star spins, it changes how the star cools. And the cooling history of a neutron star is another observable that carries information about the interior. When nucleons form Cooper pairs, they open an energy gap in their excitation spectrum. Below the critical temperature, it takes a minimum amount of energy to break a pair apart and create unpaired particles. This gap has direct consequences for the star's heat capacity and its neutrino emission rate, the two factors that control how quickly the star cools. Heat capacity measures how much thermal energy a system can store at a given temperature. In a normal Fermi gas of unpaired nucleons, the heat capacity is proportional to the temperature. As the temperature drops, the heat capacity drops linearly. But when Cooper pairing sets in and a gap opens, the heat capacity changes dramatically. Just below the critical temperature, pairing actually causes a brief spike in heat capacity, a sudden increase associated with the phase transition itself. This is analogous to the specific heat anomaly seen in ordinary superconductors at their transition temperature. But as the temperature falls further below the critical point, the gapped particles become progressively harder to excite. The number of thermally excited unpaired particles decreases exponentially, and the heat capacity drops much faster than it would in a normal fluid, falling exponentially rather than linearly. The paired superfluid can store less thermal energy at a given temperature than the normal fluid could. This means that once pairing is established, the star has less thermal inertia. It responds more quickly to changes in its energy balance. Neutrino emission is even more profoundly affected. Neutrino radiation is the dominant cooling mechanism for neutron stars during the first million years or so of their lives. Various nuclear processes inside the star produce neutrinos that escape freely, carrying energy away. The most important of these processes involve neutrons, protons, and electrons interacting through the weak nuclear force. The rate at which these processes produce neutrinos depends on how many particles are available to participate. In a normal unpaired fluid, all the nucleons near the top of the Fermi Sea are available. But when pairing opens a gap, the number of available participants drops exponentially below the critical temperature. Fewer unpaired particles mean fewer neutrino-producing reactions. The neutrino emission rate is suppressed, sometimes dramatically. This suppression slows the cooling. A neutron star with a fully developed superfluid gap cools more slowly than it would if the matter were unpaired, because the dominant cooling channel has been partially shut down. The effect depends on the size of the gap. A large gap suppresses neutrino emission strongly. A small gap suppresses it only modestly. But there is a complication. At temperatures just below the critical temperature, when pairs are first forming, there is an additional neutrino emission process that does not exist in normal matter. The formation and breaking of Cooper pairs itself produces neutrinos. As pairs form, they release binding energy, and some of that energy goes into neutrino pairs. This pair breaking and pair forming process can actually enhance the cooling rate temporarily right around the critical temperature before the exponential suppression takes over at lower temperatures. The net effect on cooling depends on the interplay between the suppression of standard processes and the enhancement from pair processes, and this interplay depends sensitively on the size and type of the gap. This is where observation becomes crucial. In 2011, astronomers announced a remarkable result. They had measured the real-time cooling of the neutron star at the center of the Cassiopeia A supernova remnant. Cass A is one of the youngest known neutron stars, roughly 340 years old, based on the estimated date of the supernova that created it around the year 1680. Because it is young and relatively nearby, about 11,000 light-years from Earth, it is one of the few neutron stars whose surface temperature can be measured with reasonable precision using X-ray telescopes in orbit. The way this measurement works is conceptually straightforward, but technically demanding. The hot surface of a neutron star emits thermal radiation, predominantly in X-rays because the surface temperature is so high, typically around 1 to 2 million Kelvin for a star of this age. By collecting X-ray photons from the star and fitting the observed spectrum to theoretical models of a neutron star atmosphere, astronomers can estimate the surface temperature. The Chandra X-ray Observatory, one of the most sensitive X-ray telescopes ever built, observed Cas A repeatedly over a span of about 10 years. From 2000 to 2009 and beyond, each observation provided a temperature estimate, and when those estimates were compared, a trend emerged. The surface temperature was dropping, not by a dramatic amount, but by a few percent over the decade of observations. A few percent might not sound like much, but for a neutron star that is 340 years old, this rate of cooling was significantly faster than standard theoretical models predicted. A neutron star of that age should have already settled into a slow, gradual cooling trajectory. The rapid drop suggested that something had recently changed inside the star. Something had altered the cooling physics. Several groups of theorists independently proposed the same explanation. The neutron superfluid in the core of the Cas A neutron star had only recently formed. The star had just cooled through the critical temperature for neutron Cooper pairing in its core, perhaps within the last few decades. If so, the pair-breaking and pair-forming neutrino emission process that occurs right around the critical temperature would produce exactly the kind of enhanced cooling observed. The star was, in effect, going through its superfluid phase transition in front of our eyes. We were watching quantum mechanics switch on inside a collapsed star in real time. If this interpretation is correct, it would represent the first direct observational evidence of a superfluid transition happening inside a neutron star, not inferred from glitches, not deduced indirectly from spin behavior, but seen directly in the thermal evolution of the star's surface emission. It would also provide a measurement of the critical temperature for core neutron pairing, a quantity that theorists have argued over for decades, pinning it to a narrow range near a few hundred million Kelvin for the densities present in the Cas A core. This interpretation remains debated. Some researchers have questioned whether the observed temperature decline is statistically robust, given the uncertainties in X-ray spectral fitting. Others have proposed alternative explanations involving changes in the star's carbon atmosphere or adjustments to the theoretical models of heat conduction through the crust. The question is not settled, but the Cas A observations illustrate a crucial point. The cooling history of neutron stars is sensitive to whether superfluidity exists when it turns on and how strong the pairing gap is. Careful measurements of neutron star temperatures at different ages can constrain the properties of the superfluid, complementing the information we get from glitch observations. And if the superfluid interpretation of Cas A holds up under further scrutiny, it would stand as one of the most remarkable observations in modern astrophysics. A direct glimpse of quantum mechanics reshaping the interior of a star. Now let me address the role of the superconducting protons, because their presence adds another layer of complexity to the interior physics. In the outer core, protons are expected to form their own Cooper pairs, creating a superconducting state. A superconductor expels magnetic fields from its interior, or more precisely, it confines magnetic flux into quantized structures. In a type 2 superconductor, which is what the proton fluid in a neutron star is expected to behave as, the magnetic field is not expelled entirely. Instead, it is concentrated into discrete filaments called flux tubes. Each flux tube carries exactly one quantum of magnetic flux, just as each superfluid vortex carries exactly one quantum of circulation. The neutron star's magnetic field, which can be enormously strong, reaching 1,000,000,000,000 times the strength of Earth's magnetic field or more, would be threaded through the superconducting proton fluid in the form of these quantized flux tubes. The number of flux tubes depends on the total magnetic flux through the star. For a typical pulsar magnetic field, the number of flux tubes is enormous, comparable to or exceeding the number of superfluid vortices. And here is where things get particularly interesting. The neutron vortices and the proton flux tubes coexist in the same region of the star. They are both thread-like structures embedded in overlapping quantum fluids, and they interact. The details of this interaction depend on the relative orientation and spacing of the two sets of filaments, and on the magnetic and nuclear forces between them. In some configurations, vortices and flux tubes may become entangled, crossing each other and creating a complex web of interacting quantum filaments. The force required to move a vortex through a tangle of flux tubes may be different from the force required to move it through the crust lattice alone. This interaction could affect the dynamics of vortex unpinning and therefore the characteristics of glitches. Furthermore, as the neutron star spins down and vortices move outward, they may drag flux tubes with them. If vortex flux tube coupling is strong, the outward migration of vortices during spin down would also push magnetic flux outward, gradually changing the star's magnetic field structure over time. This could explain some of the long-term evolution of pulsar magnetic fields that astronomers have observed. Alternatively, if the coupling is weak, vortices and flux tubes may move relatively independently, with different consequences for field evolution. The interplay between superfluid vortices and superconducting flux tubes is one of the most theoretically challenging aspects of neutron star physics. It involves two coupled quantum fluids, each with its own set of quantized filaments, interacting through forces that depend on poorly constrained nuclear and electromagnetic properties. Progress has been steady but slow, and many questions remain open. Let me now step back and address honestly what we do not know, because for all the elegance of the superfluid vortex picture, there are deep uncertainties that pervade every aspect of this story. We do not know the exact critical temperatures for neutron or proton pairing. Different calculations using different models of the nuclear force and different many-body techniques give results that can differ by factors of 10 or more. This uncertainty propagates into every prediction about glitch behavior, cooling rates, and magnetic field evolution. We do not know the exact mechanism by which glitches are triggered. Vortex unpinning in the inner crust is the leading model, but it is not the only possibility. Starquakes, sudden fractures in the rigid crust caused by accumulated stress from spin down or magnetic field evolution, could also trigger angular momentum transfer. Some glitches might be caused by a combination of mechanisms. The relative importance of different triggers may vary from star to star, and even from glitch to glitch within the same star. We do not know what is happening in the inner core. If the deepest interior contains exotic matter, hyperons, deconfined quarks, or other phases, the superfluid properties of that matter are almost entirely unknown. Hyperons might pair, or they might not. Quark matter might exhibit color superconductivity, a form of pairing among quarks that is theoretically predicted, but has never been observed. The properties of these exotic phases, if they exist, would affect the star's total moment of inertia, its cooling rate, its maximum possible mass, and its response to rotational and magnetic stresses. But we currently have very little observational constraint on what happens at the very center. We do not know whether every neutron star develops a superfluid interior. The critical temperature depends on density, and the density profile depends on the star's mass. It is possible that the most massive neutron stars, those near the maximum mass before black hole collapse, have central densities so high that pairing is suppressed entirely. If so, the most massive neutron stars might have non-superfluid cores surrounded by superfluid mantles. Conversely, lighter neutron stars might be superfluid throughout. We do not have enough data to resolve this question conclusively, and we cannot directly image any of this. We cannot see the vortices. We cannot photograph the superfluid. We cannot watch flux tubes rearrange. Everything we know about the interior of a neutron star comes from indirect evidence. Timing data from pulsars, thermal emission measurements from cooling neutron stars, gravitational wave signals from neutron star mergers, theoretical models constrained by nuclear physics experiments at much lower densities. We're assembling a picture from shadows and echoes, not from direct observation. But the indirect evidence is powerful, and it is getting better. Modern radio telescopes can time pulsars with nanosecond precision, catching glitches as they happen and tracking the recovery with extraordinary detail. X-ray observatories in space, like the instrument called NITER, mounted on the International Space Station, are measuring neutron star masses and radii with unprecedented accuracy, constraining the equation of state that governs the relationship between pressure and density in the interior. Gravitational wave detectors have already observed neutron star mergers, and the tidal deformation of the stars during those mergers carries information about the internal stiffness and composition. Future gravitational wave observations will provide even tighter constraints. Each observation narrows the range of possibilities, eliminating some theoretical models and supporting others. Slowly, piece by piece, we are building a coherent picture of what exists beneath the crust. And here is what makes this pursuit so extraordinary. A neutron star's interior is the only place in the universe where matter exists at several times the density of an atomic nucleus, cold enough for quantum pairing to operate and accessible to observation through the star's rotation, temperature, and gravitational interactions. No laboratory on Earth can compress matter to these densities. No particle accelerator can produce cold, dense matter. The interior of a neutron star is a natural laboratory for physics at the extreme frontier of the nuclear force, and the superfluid phenomena we have discussed tonight are the primary way that laboratory communicates its results to us. Every glitch is a data point. Every cooling curve is a constraint. Every pulse arrival time, measured to billionths of a second, is a measurement of conditions that exist nowhere else in the observable universe. The neutron star does not reveal its secrets willingly. It hides them beneath a rigid crust, behind intense magnetic fields, inside a gravitational well so deep that space-time itself is distorted. But it cannot hide them completely. The rotation leaks information through glitches, the temperature leaks information through surface emission, the mass and radius leak information through gravitational effects. And patient, careful observation, combined with ever-improving theoretical models, is gradually decoding these messages. What we have explored tonight is a chain of physics that stretches from the quantum to the cosmic. It begins with the pairing of individual neutrons, particles smaller than an atom, forming delicate quantum correlations mediated by the strong nuclear force. Those pairs create a superfluid condensate that stretches across kilometers. That condensate organizes its rotation into trillions of quantized vortices, each thinner than an atomic nucleus but extending the full diameter of the star. Those vortices pin to the crystal lattice of the inner crust, lock in the superfluid's rotation in place while the crust decelerates. Stress builds until the pinning fails. Vortices unpin. Angular momentum transfers. And the star, an object more massive than the sun, lurches. Its rotation jumps by a measurable amount, and we detect that jump from thousands of light years away in the timing data of a radio telescope on the surface of the Earth. A quantum event, a change in the arrangement of subnuclear vortex filaments, produces a macroscopic, astronomical observable. The smallest scale of physics connects to the largest. The rules that govern particles far too small to see determine the behavior of objects so dense and so extreme that they warp the fabric of space-time around them. And we, sitting on a small planet orbiting an ordinary star in a quiet arm of the Milky Way, can detect it, measure it, and begin to understand it. This may be the largest quantum phenomenon in the known universe, a superfluid condensate spanning kilometers, composed of trillions upon trillions of paired neutrons, rotating through an array of quantized vortices so numerous they outnumber the stars in a galaxy. And it is hidden inside a sphere only 20 kilometers wide, buried beneath a crust of nuclear crystal, accessible only through the faintest whispers in the timing of a distant pulse of radio light. We are still far from a complete understanding. The composition of the deepest core remains one of the great open questions. The exact nature of the pairing, the strength of the gaps, the mechanism of each glitch, the role of the magnetic field, all of these are works in progress. Decades more of observation and theory will be needed before the picture comes into sharp focus. But the broad outlines are emerging. A neutron star is not just a dead remnant. It is a living quantum system, an object where the most fundamental rules of physics operate on an astronomical stage. A place where matter behaves in ways we are only beginning to comprehend. And the next time someone tells you that quantum mechanics only matters at the scale of atoms and molecules, that it has nothing to do with the world of stars and galaxies, remember this. Somewhere out there, in the darkness between the constellations, a neutron star is spinning. Its crust is decelerating, slowing by trillionths of a second every day. Deep below that crust, a superfluid of paired neutrons is threaded by trillions of quantized vortices, pinned to a lattice of exotic nuclei, storing angular momentum that the crust lost long ago. The stress is building. The forces on each vortex are growing, and one day, maybe tomorrow, maybe a year from now, those vortices will break free. The star will glitch, and a radio telescope on Earth, pointed at just the right patch of sky, will record the moment that the quantum interior of a collapsed star reached out across the light years and left its mark in our data. That is the superfluid core of a neutron star. Hidden, extreme, quantum, and waiting to be understood.